The new topic is entitled Measure of Variance. There's a couple of formulas we have to talk about. The standard deviation of a sample and the standard deviation for a population. Population uses a Greek letter. The sample does not use a Greek letter. In fact, the symbol for standard deviation is just S and for a sample, and the standard deviation for a population is the Greek letter sigma. And there are two ways to compute this standard deviation of a sample. One way is you add up x minus x bars squared divided by n minus 1. Take the square root of that, or you take the square root of n times the summation of what I just wrote minus the summation of what I just wrote. Find that summation and then square it. And this gets divided by n times n minus 1. There's something called the variance. The variance is just what's underneath the square root sign. If you square this, you get s squared. If you square the other equal sign, the other side of the equal signs, you just get what's underneath the square root signs. You get that, and you get this. These are two ways of calculating the variance. Just don't take the square root. If you have the variance and you want the standard deviation, take the square root of it. You'll get S. You'll get the standard deviation. If you have S, by all means, square it, and then you'll have the variance. If you square S, well, S means the standard deviation. If you square it, you get the variance. And the formula for the standard deviation for a population is the summation of x minus mu squared divided by capital N. Capital N is just their sample size of the entire population, or their entire population size. And the variance, just square it. Square the standard deviation. If you square sigma, you'll have the variance, which is just the summation of x minus mu squared divided by n. If you have the standard deviation, you square it, you'll have the variance. If you have the variance, you just take the square root and you'll get the standard deviation. Okay, so I'm going to give you some data. I'm going to ask to find the standard deviation and the variance. Give you very simple data. Find the standard deviation and variance for this sample. And the sample is just 2, 5, and 11. So x bar, well, you add them up. You get 18 divided by the three numbers. X bar is 6. Now, we'll use the first formula. We need to calculate x minus x bar. Well, we have x. We have the x's. We have the x bars. They're always the same. And now we can compute. Well, first we'll compute x minus x bar. And then I'll square it. Because that's what I have to add up. Before I can add up stuff, I have to have that stuff. X minus x bar. 2 minus 6. 5 minus 6. 11 minus 6. Now I square these numbers. 16, 1, 25. And I add them up. I get 42. That's the summation of x minus x bar squared. That's a long way in finding the standard deviation, which is the summation of x minus x bar squared divided by n minus 1 square root. Well, I have the numerator. It's 42. And n was 3. N is a number of numbers. There's 3 numbers. Take away 1, that's 2. So I get the square root of 21. And the variance is denoted by s squared. If you square this, well, then you have to square that. The variance is 21. And you need to be mature enough where you're just given this to know that you need to complete this table. You need an x bar. You need a heading for x and a heading for x bar. Why? Because then you can subtract them. Then you can subtract x minus x bar. And then you have to square it. So I took all the numbers in this column and I squared them. X minus x bar squared. Negative 4 squared is 16. Negative 1 squared is 1. 5 squared is 25. And I added them up. I got exactly what I wanted. I got the summation of x minus x bar squared. Let's write that down a little bit more neatly. I add up these numbers, and I'll get the summation of x minus x bar squared, which happens to be 42. Okay, you need to do some of these. Now, I suggested that we do this, we're going to do the same problem all over again, almost forgot, using the alternate formula. Okay, there are 2 formulas to calculate this mean. Excuse me, to calculate the standard deviation. Okay, so now we're going to use this formula. S is equal to the square root of n. N is 3. Times the summation of x squared. Well, the x's are 2, 5, and 11. Well, I need x squares. 2 squared, 5 squared, 11 squared. So if I add these up, I get 150. Well, that's the summation of x squared. Okay, plus times the summation of x squared times 150 minus the summation of x squared. Well, the summation of x is 18 divided by n, which is 3, times n minus 1. And there it is. 3 times 150 is 450. 18 times 18 is 324. 324 divided by 3 times 2, which is 6. The square root of that. When you do the subtraction on top, get 126 over 6. The 6 goes in there 126 21 times. So you get the square root of 21. Exactly what we got before. So if s is the square root of 21, then s squared, if I square the left side, I have to square the right side. Some people love this formula. They think it's easier. In fact, it is easier so long as you don't confuse this and that. If you're going to confuse those two, use the longer formula over here. If you're not going to confuse these two, then this one's much easier. All I had to do was square the x's and add them up. All I had to do was add up the x's and then square it. I didn't have to find the mean. I didn't have to find x minus x bar for every data. In our case, there's only 3 datas, 3 points of data. So it wasn't so bad. But when you have 10 points of data, you don't want to compute x minus x bar 10 times and then square it. My advice is to use the second formula and not to make those silly errors. Now, here's a really good rule that students should know. It's called the empirical or, what is it, 68, 95, 99.7 rule. And this is for data with a bell-shaped distribution. Bell-shaped distribution means if you plot the data, it looks like a bell-shaped curve. So we have these three following facts. About 68% of the data is within or falls within one standard deviation of the mean. About 68% of the data falls within one standard deviation of x bar. About 95% of the data falls within two standard deviations of the mean. And about 99.7% of the data falls within three standard deviations of the mean. What does that mean? If x bar is 70 and the standard deviation is 5, so here's the mean. What does it mean to fall within one standard deviation of x bar? That means you can go at most 5 to the right and at most 5 to the left. And about 60% of all the scores will be in there. If the let's just make the average 50, excuse me. The average doesn't have to always be 50. Well, let's actually live with 70. So you add 5 and you take away 5. You add one standard deviation to 70. Another name for standard deviation in this problem is 5. And you take away 5. About 68% of the data lies in there. Now, if we go 2 standard deviations, we go 5 to the right and then 5 to the right again. That brings us to 80. Within, that means we can go 2 to the left. Within 2 standard deviations. If you're between 60 and 80, 95% of the scores will be in between there. If you go 3 standard deviations, you go 5, 5, and then 5 again. 85. 1, 2 standard deviation, the third one. 55. Between 55 and 85, almost all the data, close to 100% of the data will be between 55 and 85. Just take the mean and add the corresponding number of standard deviations, or subtract. X bar plus 3 standard deviations. Well, it's 70 plus 3 times 5. That's 15. That's 70. You add, get 85. X bar minus 3 standard deviations. That's 70 minus 3 times 5. That's 55. If you're between 55 and 85, well, 3 deviations. 99.7, about 99.7% of the data, almost all of it, will be between 55 and 85. That is, if you got below 55, you did really, really poorly on this exam, assuming it's an exam. If you got over 85, you did really, really well on this test. If you got between 65 and 75, you were average. More than 2/3 of the people got in there. You're an average student. Get above 75, between 75 and 80, you're an A student. Above 80, you're amazing. And 90, you beat out 99.5.6% of the people. Get over 85, you really aced the test. Now, before you can use this empirical rule, you have to be told that it's a bell-shaped distribution. You have to be told that it is a bell-shaped distribution. You're not told that, don't be talking about the empirical rule. It's a new rule we're going to talk about now. It's called Chebyshev's. Chebyshev's theorem. Chebyshev is a famous mathematician. It goes on to say this. It goes, the proportion, I guess, or fraction, the proportion of any set or data. So notice it's not saying that it has to be bell-shaped. Another name for bell-shaped, you'll learn this soon enough, is called normal. It's normal. It's a normal distribution. The proportion of any set of data, and this is a very powerful theorem, lying within K standard deviation of the mean is always at least 1 minus 1 over K squared, where K is any positive number greater than 1, where K is any positive number greater than 1. Now, if K is 1, 1 squared is 1, 1 over 1 is 1, 1 minus 1 is 0. So, of course, the proportion is bigger than 0, bigger than or equal to. All right. What is this saying? The set or data lying within K standard deviations of the mean. Here is the mean. Let's go out 1, 2 standard deviations. This is X bar plus 2 standard deviations. This is S and another S. And you can, within, that means you can go to the left as well. You can go S to the left 2 times. So this is X bar minus 2S. What proportion of data lies within it? It's going to be at least 1 minus 1 over K squared. But K is the number of standard deviations. K we're saying is 2. That's k right there. We're going 2 standard deviations to the right and to the left. 2 squared is 4. 1 minus a quarter is 3/4. So it leaves 3/4 of the data is in between. Now, the empirical rule will tell us 95%. Well, if it's this is 75%. It says at least 75. Well, 98 is true. But remember, empirical is only true for a bell shape. This is true for any shape, any bizarre shape. The distribution can look like that. And if here's the mean, and this is 2 deviations to the left, and this is 2 to the right, the chances that you lie in here, you got a score in there, will be at least 75%. Every time. Every time. If you only want to go 1 standard deviation, say in between here I went s to the left of the mean and s to the right, the chances that you end in there, well, k should be bigger than 1. Or let's go 3 deviations. 1, 2, a third one to the right, and 3 to the left. 1 to the left, a second standard deviation to the left, and a third one. So this is x minus 3 standard deviations. This is x plus 3 standard deviations. What part of their scores, what can you tell me about the scores that lie in there? Well, it's 1 minus 1 over k squared. K is now 3. K is a number of standard deviations away from the mean. So it's 1 minus 1 over k squared. 3 squared is 9. 1 minus a ninth is 8 ninths, which is approximately 89%. So I can guarantee you that at least 89% of the data, regardless of the distribution, whether it's bell shape or not bell shape, whether it's multimodal or bimodal, it's going to have at least 89% of the data. Now, I want to talk about notation. I want to know what are the chances that x bar lies in between x bar minus a number of standard deviations, k standard deviations, and x bar plus some number of standard deviations. And I don't know why the x bar wasn't in the middle, because I put it there. In fact, so let's just call that x. If I take away x bar from all 3 sides, I get negative ks is less than x minus x bar, which is less than ks. Let's just call that y for a moment. If y is in between, say, negative 3 and positive 3, that means the absolute value of y is less than 3. Since this and this just differ by a negative sign, you can say this. That's what Chebyshev is saying. The probability that a score and a mean, the absolute value is less than ks, is at least 1 minus 1 over k squared, where k is bigger than 1. Okay, so that's what it's really asking. what's the chances or probability that you are within k standard deviations of the mean? It's one. You would write it this way. Your teacher will tell you if he or she really wants you to write it down. But most importantly, it's at least, it can equal. If I make at least $10 an hour, I'm like, I hope I get a job that pays at least $10 an hour. So if I get a job that pays $10 an hour, I'm going to say, well, I lived up to what I wanted. That is, 10 is at least 10. 12 is at least 10 as well. Right. It's 1 minus 1 over k squared. You get at least that proportion. You get 9 out of 10. And when k get, k is only good for 2 or 3. I mean, if k is 4, you get 1 minus 1 over 4 squared, which is 1 minus the 16th. Think of this 1 as 16 over 16, and you take away 1 over the 16, you have 15 over 16. That's more than 90%. I mean, 16 into 15. 9 is 144, 6. Bring this down. Goes 3. Okay, 48. It's a little bit smaller than I thought, but it's still pretty large. It's like 7. It's over 93%. 93.7%. So it grows rapidly, but it's good because it doesn't, Chebyshev inequality is good because it doesn't dictate what kind of population, what kind of distribution you should have. It doesn't need to be what's called normal. So let's just look at another example. Suppose I tell you on a test the average is 100 and the standard deviation is 15. What can be said about Chebyshev's theorem when k is 2? When k is 2, what can you say? You should say that you get at least 1 minus 1 over 2 squared. 1 minus a quarter, which is 3/4, or 75%. That is 75%, at least 75% of the students, for example, lie within 2 standard deviations. Here's 15. Excuse me, here's 100. Standard deviation is 15. So I go 15 and 15. That brings me to 130. I go back 15 and 15. That brings me to 70. Chebyshev guarantees me in here is 75% or more. And I made one little bit sloppy mistake. Doesn't matter what kind of distribution you have. If the mean is right here, and here's 70, and here's 130, well, at least 75% of the scores lie in there. It might be less, but it will never, ever, ever be lower. And if it is lower, Chebyshev's theorem is wrong. And since I know how to prove it, and since it's been around for a couple of centuries now, it's true, it works. Okay, so suppose we have this problem. I'm going to list intervals between train arrivals at a particular station. And, in one given day you had to wait 9.8 minutes and then 9.2 minutes. See if this mark is any better. No, it's not. It's not a good sign. You can see it on the computer screen, but I can't see it on my physical board. Okay, 9.0 minutes, 8.7, 9.6, 9.0, 6.5. You had to wait 9.2 minutes for the next train, then 9.5 for the next train, and then 9.3 and 9.8 and 9.4. And the question is a 10-minute wait unusual? Is it unusual to wait 10 minutes? Okay. Well, if you add up these numbers, which I've already done, minus some silly error, I claim they add up to 108, and there's 12 numbers. So the average wait time is 9 minutes. Now, remember, the variance is x minus x bar squared, the summation of that. And then you divide by 11. 12 minus 1, which is 11. I mean, you can make up your table. You can do it in your head. This number minus that is 0.8, and it gets squared, plus this number minus 9 is 0.2, and you square it. This number minus 9 is 0. You square it, you get 0. I won't bother with that. This number minus 9 is 0.3. Oh. This number is 7, not 9. This number here is 7. So when you subtract, you get negative 2, and when you square it, you get 4. This number minus 9 is negative 0.3. But when you square it, it doesn't matter if you write negative or positive. This minus 9 is 0.6. You square it. This minus 9 is 0. You square it, you get 0. This number minus 9 is negative 2.5. It's the same as squaring 2.5. This number is 0.2 above. This take away 9 is 0.5, and you square it. And that whole sum gets divided by 11. And if I added up the top correctly and I divide by 11, I get 0.73. Okay, that is s squared. The standard deviation is the square root of 0.73, which is 0.84, approximately. So that's the standard deviation. We did all of that to find the standard deviation. I'm going to erase most of this. We have the average, and we have the standard deviation, 0.854. Is it unusual to wait 10 minutes? Well, the mean is 9, and here is 10. Well, if you go one standard deviation, you'll be at 9 plus 0.854, which is 9.854. 9.854. This is one standard deviation. If you go another standard deviation, that is, you add on 0.854. Another standard deviation, you'll get to 10.708. So what you know is that you're less than 2 standard deviations away. You're less than 2. You're between 1 and 2 standard deviations away. which is not a lot. Which is not a lot. Oh, how come the line didn't draw? I'm sorry. Let me try that again. Here's the average of 9. You go 1 standard deviation. That brings you the 9.854. You go another, which is below 10. You go another standard deviation. That brings you the 10.708. So 10 is somewhere in the middle. It's more than 1 standard deviation away, but less than 2. It's within 2. That's not bad. Okay, it's not unusual. It's not unusual. Chebyshev will tell you that 1 minus, that you have a greater than or equal to, at least, 1 over 1 minus 2 squared, which is 75% of being within 2 standard deviations. Okay, it's fairly common to be within 2 standard deviations. So it's not unusual, no. The answer to the question is no, it's not unusual. It's not unusual. When it's unusual to be 3 or more standard deviations away. Now, the next and last thing I'm going to talk about is the z-score. The z-score is the number of standard deviations, a data point which is called x, a data point x is from the mean. The z is the number. Well, if x bar is 50, and this x is 70, and S, the standard deviation is 10. Well, how many standard deviations is this number from the mean? Well, 50. You go 10, that brings you to 60. I'm going 10 because that's the standard deviation, 60. And you go another 10, you get to 70. So the answer is 2. Well, an easier way of doing it is to find the distance, which is 20, and then divide by 10. I want to know how many, why was the standard deviation 2? Because there were 2 10s in 20. You take the number of 20s, you take 20, divide it by 10, you'll get 2, which is the z-score. That is, using this rule right here, z is equal to x, the 70 was x, minus the 50 was x bar, divided by 10, which is sigma. That's the formula to finding the z-score. So using this piece of information and a score of 78, what would the z-score be? So all you know is the mean is 50, x here is 78, and the question is, what's the z-score? This is x bar, and this is some x, and 10 is the standard deviation. So we want to find out what's the z-score? Now sometimes z-scores are negative. That just means x is to the left of the mean. Using our friendly formula here, z is x minus mu divided by sigma, which is 28 divided by 10, which is 2.8. Now, if I wanted to know the z-score at 22, so this was z at 78. We don't want to write z equals and get different numbers. How can z equal different numbers? they're different z's. This is z at 22. It's x, which is 22, minus the mean divided by 10. This is negative 28 over 10. That's negative 2.8. They're not the same, but they just differ by a sign. And the reason is from 50 to 78, I went 28 to the right, excuse me, and then I went 28 to the left. 50 minus 28 is 22, and 50 plus 28, 78. It's symmetrical, except the signs will be different. So don't have a panic in case you get a negative z-score. Now, this was for sample. The z-score, the formula for the z-score for a population, it's the same formula, except the way we write the mean for a population is mu, and the way we write the symbol for standard deviation has changed. It's now sigma. Okay, that completes the section on measure of variance.